Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about vector functions and space curves. So let's just hop right into it. So here we're going to be looking at vector valued functions. Apparently this is a thing. Okay, so for vector valued functions, in general, a function is a rule that assigns to each element in the domain an element in the range. So we have a function and we have a domain and we have a range. And so we assign each element in the domain to its corresponding range. So basically an f of x equals y, where this x is the domain and this y is the range. A vectored valued function or vector function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. So that's interesting. We have a set of vectors. We're most interested in vector functions R, whose values are three-dimensional vectors. This means that for every number t in the domain of R, there's a unique vector in V3 denoted by R of t. If f of t, g of t, and h of t are the components of the vector R of t, then v, g, and h are real valued functions called the component functions of R. And we can write R of t. Okay, basically, here's a vector function. It has a set of real numbers, which is the domain, and a range, which has a set of vectors. We are most interested in vector functions are three-dimensional vectors. Okay, for every number t, I'm just rereading it so that I get. In the domain of R, there's a unique vector in V3 denoted by R of t. Are real valued functions called the component functions of R. So here's what a vector valued function looks like. R of t is equal to component functions f of t, g of t, h of t. And we can write this as, well, we can write this in ijk. Right? So f, g, and h are real valued functions called component functions. And we use the letter t to denote the independent variable because it represents time in most applications of vector functions. Okay, let's just dive straight into an example. So trying to wrap my head around what exactly does this do. So let's say if we have a vector valued function, r of t, which has components t cubed, natural log of 3 minus t. So these are all pre-calculus stuff. And square root of t. So these are all functions, right? So if we have this, then our component functions are basically all of the ones inside the vector function. So inside the vector, we have functions. So I think that's what it means. So we have f of t, which is t cubed. We have another function we'll call g, which is natural log of 3 minus t. And we also have another one, h of t, which is square root of t. So those are the three component functions that we have. And usual convention is that the domain of R consists of all values of t, right? So R, the domain is that R has all values of t. So I'm gonna just write like domain of R is t which contains any real number. So the expressions t cubed, ln of 3 minus t, and square root of t are all defined when 3 minus t is greater than 0, because that's for natural log, and t greater than or equal to 0. So here we want to restrict our domain. So that's what we want to do, right? So t cubed ln of 3 minus t and square root of t are defined when anything inside the natural log, so 3 minus t is greater than 0. It can't be equal or less than 0 because that would be undefined. And t greater than or equal to 0. This is for the square root of t expression or function, because we cannot get a square root of a negative number because that would be imaginary complex numbers, right? So here we have the means. Therefore, domain is the domain of our vector function is the interval 0, 3. Right? So it's in between 0 and 3, but 3 is exclusive. Because if it's equal to 3, it would be 0. And we don't want that. Okay. Now we talk about limits and continuity. So what about limits and continuity? This is from a previous calculus course, Calc 1, where we want to get the limit of something. So here the limit of a vector function R is defined by taking the limits of its component functions as follows. So here's the, I'm not going to say formal definition because I'm still not yet sure. But if we have a vector valued function, which has components that are different functions, then we say the limit of our vector function as t approaches some a I'm assuming is asymptote. Asymptote meaning we don't intersect some axis. Then, we're actually also taking the limit of the other functions here. So we're not just taking the limit of R, but we're taking the limit of these other functions. And that will give us our limit of RFT, I'm assuming. Oh, messy handwriting. H. So the idea is if we take the limit of a vector function, then we also have to take the limit of its component functions. So that's the big idea. Okay. And okay, there's some epsilon definition, which I'm not going to go in depth because that's theory based. But okay, let's just go to an example real quick just to apply what this definition is. So we're going to look at example 2. And here we're being asked to find the limit of our vector function as t approaches 0. And here, R of t is equal, I'm actually going to put this down. So here we're saying R of t has these components. So here you can see that these are all different kinds of functions. Sine of t over tj, okay, right? And so we're just going to take the limit of each components. Of each component functions, and that will give us what we need, right? So let's write it formally. If we take the limit of our vector function, then we're going to take the limit of each of our component functions. So t cubed I, we're adding that to the limit of t e to the negative t, as well as our sine function here. So this is sine of t over t. K, j, right? Which is actually just I plus k. Why? If this goes to 0, then this whole thing is 1. As t goes to 0, we have 1 plus 0, so that's 1. What else? As this goes to 0, well, then this is just 0. This is 1. 1 plus 0. And then as this goes to 0, we again have 1. Right? I'm not going to explain this in depth because this is a Calc 1 course, but it's this idea of just taking limits of functions. So 1 plus 0 plus 1. So we would have 1i plus 0j plus 1k, which is just I plus k. So that's the idea. Okay. Now we have this idea again. So we talked about limits. Let's talk about the concept of continuity. So a vector function R is continuous. This is like Calc 1 all over again. Continuous at A if the limit of our vector function as t approaches some value A is just R of A. Right? This is a Calc 1, this is a Calculus 1 concept. So in view of definition 1, we see that R is continuous at A if and only if its component functions are continuous at A. So what does that mean? Well, our component functions should also be continuous. So it's not just R of A if we take this definition, right? Okay, let's talk about, so this is the new topic. Let's talk about space curves. Even I don't know what this is. So about space curves, it says there's a connection between continuous vector functions and continuous space curves. So suppose that we have 3 different functions. They're continuous real valued functions, and they're on an interval I. Okay, let's just write that real quick. So suppose we're given three functions. So let's say f, g, h are continuous real valued functions. Then what do we, yeah, on, okay, on an interval, let's say some interval I don't know, then the set of all points x, y, z in space. Oh, so that's what this is. And the set, okay, we'll just name the set. Let's name it C. That contains all arbitrary points, I don't know, some points x, y, z in space. So set C, which contains these points in space. Space means 3D space, where, so another important note is that f is the output of our function f, y is the output of g, and h is the output, z is the output of h. So what this is trying to say is that if we have continuous three different functions on some interval, then we have some set of points in space. So this is our 3D space, right? With our x, y, and z. We have some x, y, z point here. This is just random. We should be able to get this if we plug in f of t, g of t, and h of t. So that's the idea in theory. And t varies through the interval I. Throughout the interval I is called a space curve. So it's a curve, but in space. Not a curve in a plane, it's a curve in space. So if we draw our thing here again, then that's a space curve, the red thing. Okay, so I bet we'll use parametric equations of some sort. Oh, okay, I'm right. So the equations in 2, so the one I just did here, they're called parametric equations of C, and T is the parameter. We can think of C as being traced out by a moving particle whose position at time t is f of t, g of t, and h of t. If we now consider the vector function, so we use our vector function r, then r of t is the position vector of the point P on C. Thus, any continuous vector function r defines a space curve C that is traced out by the tip of the moving vector r as shown in this figure. So I'm going to show that real quick. But the idea is our vector function r is a position vector. And so if it's a position vector, we can actually plug in some time t and then plug in to that vector function. And then we plug that also to our component functions because R has component functions. And then that will give us whatever point we have on this set C or the space curve C. So that's the idea of that, right? Okay. So ideally, it's just parametric equations in a vector. I think that's what it is. Yeah. These things, they're parametric equations. And so they will give me the corresponding vector. So not point, sure, they'll give me a point, but they will give me a corresponding vector. They can give me, I don't know, they can give me this vector, or they can give me this vector. If you notice the arrows, that's what the vector function is for. And so let's say, oh, they gave me a point here, right? And so r of t will give me this vector here. My bad, it wasn't this one. Scrap that. So we have a point here, and it will give me a position vector. That's this blue thingy. So that's the idea. Okay, so knowing that, let's move to an example. Example 3. So here, we want to describe the curve. And this curve is given by a vector function. Okay. And this vector function is r of t, which has component functions, which are parametric equations. Right? So this is a vector function. It has 3 component functions. So apparently you can put functions in vectors as well. Okay. So how do we describe the curve? Well, we can, based on this vector function, we can construct parametric equations. And what do parametric equations do again? Well, based on some t, they give you corresponding points. So we can do that. So x is this, right? Y is this. And z is this. And we can plug in something here. So we actually recognize these equations as parametric equations of a line, and it passes through a point 1, 2, -1. Now, where in the world did I see that? 1, 2, -1, right? From our previous discussion, this is an initial point, x naught, y naught, z naught. So it passes through that point, right? What else? It's also parallel to the vector 1, 5, 6 because we have our direction vector here. 1, 5, 6. So you can refer to that in a previous video, which is about equations of lines in 3D. So here we're just describing what this curve can do. Okay, so we can say this line with parametric equations passes through, let's say, P naught, which has points 1 to -1, and parallel to vector. Let's denote it as V with components 1, 5, 6. So it's a line. What else? What else can we do? Plane curves. So we talked about lines and planes. Plane curves can also be represented in vector notation, right? So we cannot only, this is actually just a line, funny enough. So we can also say something about planes here. So planes, or plane curves, can also be represented, or they can also be in vector notation, which we did do before. Pretty sure we derived it or something. So for example, the curve given by parametric equations. So I'm just gonna write, for instance, we have parametric equations, x equals t squared minus 2t. And we also have y, which is t plus 1, right? Could be described as r of t is, so this isn't 2d, t squared minus 2t, t plus 1. Then we could also write this in ijk format, but in this case it's only I and j, right? So we could do that. Here our vector I is just in 2D, 1, 0, and j is in 2D as well. Okay, let's look at another example real quick. Okay, so here we want to sketch the curve. And we have a vector equation here. Which is r of t equals, so here there's a vector valued function, or equation, I mean. So cosine of t I, I don't know why they wrote it that way. Sine of t j plus tk. So I guess the first thing we can do is we can try to find parametric equations here. Or we separate it into parametric equations. So we have x is this value here, y is sine, and z is just t. Right? Now since x squared plus y squared, so here we're using a trig identity. We observe that x squared plus y squared is just cosine squared plus sine squared is 1. Then curve is a circular cylinder, or it lies on a circular cylinder. It's circular in 2D, but here we're missing the z. So z is 0, or z can be any value. That's why it's a cylinder. So this is from a previous topic, which is about quadric surfaces. So this circular cylinder has a unit circle equation, but in r cubed. Okay. Here we say that some arbitrary point xyz lies directly above the point xy 0. And this moves counterclockwise around the circle x squared plus y squared equals 1 in the xy plane. The projection of the curve onto the xy plane has vector equation r of t. Oh, so here we're not only observing quadric surfaces, but we're actually finding some movement here, or projection of the curve, which can only be described by this vector equation. So the projection of the curve onto the xy plane has vector equation so we actually have the projection of curve is r of t, which has components cosine t, sine of t, and t. No, not t, 0. Don't know why it went from t to 0, actually. Oh, onto the xy plane. Then yeah, it's 0. XY plane. Because again, when we're in the XY plane, our z is always 0. But since z is t, then it spirals upward around the cylinder as t increases. And so we actually have a name for this. It's called a helix. And I'm just going to show real quick on what in the world am I talking about. So this vector equation, well, if this was t, then it would give us this red spiral thingy called a helix, right? So helix. That vector equation helps us identify that movement or the projection. So this is actually interesting. And a fun fact of this is DNA. So this also has a helix because the DNA, it has two linked and parallel helixes that are intertwined. And so those are examples of vector equations of curves. If you look at the DNA, right, you have two helixes there. They're both spinning around. I'm not going to go in depth to that because I'm not a biologist. So yeah. Okay, so in the next three examples, we are given a geometric description of a curve, and we're being asked to find parametric equations for the curve. So let's do that real quick. So example 5. Here our task is to find some vector equation and parametric equations. So it's kind of like finding equations of a line all over again. But this time we're doing it for vectors, vector equations. Or what do you call this? Like vector, what did I call it again? Vector functions. Okay. I was right. It was vector functions. And how are we going to do this? Well, we have some given information. So we have a line segment here. This line segment, they have a weird way of saying it. It joins the point. We'll name the point, let's say P, 1, 3, -2, to another point Q. So a different one. 2, -1, 3. Cool. So how do we go about this? We're given points, and these 2 points are in the same line segment, I'm assuming. So the line segment PQ has, well, P and Q in it, obviously, in 3D. How are we supposed to find a vector equation and a parametric equation out of it? Well, if we remember from our previous topic about equations of lines and planes, we can find a vector equation for the line segment that joins the tip of the vector R0 to the tip of the vector R1, right? So the way to do that is we want to find basically the equation of a line. So that's what we want to do. And here we're given 2 points to do that. So we want to find vector equation of line. So this is a previous topic. So let's say we have R of t, which is 1 minus t R0 plus t R1, right? And this is, well, t is in between 0 and 1 inclusive. This was from one of our examples, that idea of a vector equation for the line segment. And so we just take what we're given. So we say R naught is the initial point. So 1, 3, -2. And then R1 is the other point. So 2, -1, 3. And we're just going to apply this to our formula here. So R of t is 1 minus t. Then we have our vector. So 1, 3, -2 for R naught plus t times 2, -1, 3. So here we just plugged in what we know. And we can now simplify. So R of t could be simplified to 1 plus t, 3 minus 4t, -2 plus 5t. And again, these are both t's that are in between 0 and 1 inclusive. And so the corresponding parametric equations of this vector function. So here we find parametric equations. So here we just say, oh, we found x is 1 plus t, y is 3 minus 4t, z is -2 plus 5t. And again, we have that condition. Right? I'm actually gonna look at this for a bit because I was trying to grasp how exactly did we find these stuff. I might take a detour to 12.5 just so that I can check where I found this thing here. So if we look back at 12.5, I'm gonna quickly double check, probably equations on lines. We're given this r equals r naught plus tv. Where did we get the 1 minus t though? That's what I don't know. Let me think. Oh, there you are. Look at that. So we got it from there. So, okay. Yeah, we made like a general formula here. That's how we were able to derive this thing. So the line segment from R0 to R1 is given by this. Okay, so that's where we got it. Yeah, it wasn't obvious because I never used it too much. No, I'm gonna be honest. If you watch my videos, I don't think I ever used that formula at all in that chapter. I just used it now, as in now. So yeah, we have R0 and R1. So two vectors pointing to different points, and we can make a vector equation of that line, which we did. We got parametric equations out of it. Okay, now I know where I got it. So yeah, that's it. And we actually have a graph to go with it on what that vector function looks like. And looks like this. Okay. I like putting it somewhat downwards. So that's like a big picture here. So P to Q, plug in something to the vector function. This is the projection of the curve. It's just a line. But here we applied vector functions. Okay. Let's do another example. So here again, our task is to find a vector function that represents What does it represent? The curve of intersection of the cylinder. So here we have a cylinder, x squared plus y squared equals 1. So this is a quadric surface. And we're also given a plane. And this plane is y plus z equals 2. Okay, so we actually have figures here to show how the plane and the cylinder both intersect in 3D space. And another figure to show the curve of intersection, which is an ellipse. So I'm gonna show that real quick because I think it's gonna be super helpful. Okay, I'm gonna move my head because I'm part of the screen effect. Okay. So let's slot this. Never mind. Okay. So here's a curve of how this looks like. Here we have the circular cylinder, the quadric surface, and we have a plane curve. And here's their intersection, or their red trace, which is an ellipse. Right? Okay. Now the projection of C, so that intersection C, onto the xy plane is the circle x squared plus y squared equals 1. Okay. Which was similar to what we did in the previous example. So we know that we have parametric equations x, which is cosine t, y, which is sine t, and z. Oh, we don't have a z. So let's actually just write it down. So the projection of C onto xy plane is our unit circle, but in 3D, so z is 0. And so we write out these parametric equations of x and y. Z is 0. So we already know that. Condition being t is in between 1 revolution. So 0 to 2 pi. So a trig high school trigonometry class. From the equation of the plane, so here from the equation of the plane, where is that? Y plus z equals 2. So from plane equation, y plus z equals 2, well, we can now say, oh, z is 2 minus y, which is 2 minus sine of t. And there we have it. Those are our parametric equations. So we already have something for x, something for y, and something for z. So x is cosine, y is sine, z is 2 minus sine. And here we can, so after finding parametric equations, we can find the actual vector function or equation, doesn't matter. So we say r of t has these guys. I don't want to write them in IJK, which the textbook did. I prefer them in this notation. But we can write them in IJK, it doesn't matter. And our condition is that T is in between 1 revolution. Same here. My bad. 2 pi. Okay. So what is this equation? Well, it's called a parametrization of curve C. So it's this idea of parametric equations. Yeah, and if you notice that we have arrows in here, so these arrows here, well, the purpose of that is to indicate which direction C is traced as our parameter T increases. So if T goes to 2 pi, that's the direction that T is going, and we can get points out of that. So it's basically like a projection of a curve. That's the purpose of having this concept of vector functions. Okay, let's go to example 7. So here, our task is to find parametric equations again. For the curve of intersection. Of the paraboloid. So we already know what a paraboloid is from a previous geometry, or if you watched my other video, then you probably have seen what a paraboloid is. It's basically a 3D parabola. So we want to find parametric equations for the intersection of a paraboloid with a plane. And this plane is y equals x. So let's immediately go to a picture just so that I can show you what this is. So we have an equation of a paraboloid and a plane. There we go. Because any point on the curve C of intersection satisfies the equations of both surfaces, we can substitute y equals x into the equation of the paraboloid. So ideally and this applies to any math, if we're trying to find the intersection of two things, whether that's 3D or 2D, we just plug one of them to the other, right? So here we can just substitute y equals x, the plane, into the paraboloid for y equals x squared plus z squared, right? And this would give us like what? So if we plug in y equals x to the other thing, then we can make it 4x x squared plus z squared for the paraboloid, right? And then if we so I'm just gonna say here, what we're doing is we're finding a point of intersection. We don't have to find the entire curve intersection, because any point on that red curve, that intersection curve, any point there would satisfy the equations of both surfaces, right? And our purpose is to find parametric equations. So if we find points, then we have this initial point, right? The x naught, y naught, z naught, which we need. And then we'll worry about the others later. Okay. So yeah, now we have this, right? And then from here we can, you guessed it, completing the squares again. So we say, oh, x squared, x minus 4, no, I'm kidding, minus 2 squared plus z squared equals 4. And voila, we have our circle. We have it. This thing is basically that. At least I like to think it's that, right? Okay, okay. Now, what do we want to do now that we have that? Yeah, that's the projection of C. And y is 0, by the way. Y is 0. So it has a center of 2, 0, 0, because we got the 2 from the x part, y equals 0. And then z doesn't have anything in it, so it's also 0. And it also has a radius 2 because of this. Just the square root of that, that's 2. Circle equations. From a previous example, so based on here, this projection, we can now write, again, since we're dealing with circle equations, we can now write parametric equations, right? So here we can immediately find parametric equations. So once we have a circle equation here, oh, we can immediately find the parametric equations. So x gives me some initial point 2. I added to what? 2 cosine t, right? And then we also have z. Z is 2 sine t. Now, how did I know that? Well, again, we use the idea of the trig identity. X squared plus y squared is equal to 1. Cosine squared plus sine squared equals 1. And we just modified that. So now we have x minus 2 squared plus, sure, we can say that's z squared equals 4. So here we have something about cosine. So here we have 2 plus 2 cosine t plus 2 sine t, which is equal to 4, right? I hope I'm right, actually. Yeah, I am right, because cosine plus sine is 1, 2 plus 2 is 4. Yeah. So it's just some trig identity. Yeah, I'm just trying to wrap it around my head. And maybe you might be wondering, what is y? Well, if we look at our equation here, y is x. So whatever x is, that's what y is. So y is also 2 plus 2 cosine t. So those are the parametric equations. Yeah. Yeah, that's pretty much it for for studying this concept of vector functions and space curves. It's really all about projecting a curve, because we have vectors, and now we're now applying the idea of functions from a pre-calculus class. We're combining them together, and then now we can see how these vectors actually move, not just in a straight manner, but also in complex ways, like in a circular manner, in a straight manner, in a spiral manner like a helix. And this can definitely be seen in real life applications. So I'm definitely going to think of some applications of this, and maybe I might make videos on it just to show you how these vector functions can be seen in real life. So yeah, I hope you guys enjoyed this video, and I'll see you guys in the next one.